Third time is a charm. Using a different computer, not trying to put my face on it. Hopefully the sound will match up with the picture. And I'm so sorry for everyone who wasted their time trying to work on something. So in your lab, this is what we're trying to do here. In a normal year, you would have done this in real life. So what we have is a block here. Okay. And you can choose this type of surfaces. So in this, there's a wood block on a lab table. You can change the mass. And then this little recording force probe, which is like a fancy spring scale hooked up to a computer, is going to actually record the applied force while the person first pulls it enough until it moves, and then pulls it at a constant velocity. You have to take my word on that that's what's happening, because that's what you would have done in the lab. Now, let's take this box and move it down here and put the forces on it. And I'm going to do this real quick. All right, so we did this yesterday. There is a force of gravity acting down. Since it's on a supporting surface, there is a normal force. Remember, normal means perpendicular, so perpendicular to that surface. But also, since the block is square, it's perpendicular to the block. All right, is pushing up with a balanced force. The person pulling here is giving a force applied, and that is being resisted by a force of friction. Okay, and just remember, force frictions are always parallel to the surfaces and on contact opposite motion. Okay, so both cases where it's almost moving and where it's moving at constant speed, this is what this looks like. Okay, now the whole point of drawing free body diagrams is to write specific forms of Newton's second law. So it's the net force that equals the MA, not just a single force. But since we learned back in vectors, you can't just add things going in the x direction to things going in the y direction. We have to split this into two directions. And this needs to be done for any problem where we have things happening in two dimensions, which is pretty much every kind of friction problem. All right, so looking at my picture here, in the x direction, I can see I have two forces, force friction and force applied, and they equal to the MA in the x direction. Now, because it's either moving at a constant velocity or it's not even moving at all, this is not accelerating, all right? And it says that right down here, okay? That's because the way this lab is conducted, all right? Similarly, in the y direction, I also have two forces, a normal and a gravity. And notice I'm summing up the forces, but I certainly expect when I put numbers in to that anything down or left would be negative. I usually wait until I put the numbers in. There are times when it makes sense to say Fn minus Fg equals Ma. Just don't put the negative in twice. Like, by the time numbers are in, anything up should be positive, anything down should be negative. Anything right should be positive. Anything left should be negative. Okay. And this is certainly not even moving in the y direction, so the acceleration is also zero. So because these forces are balanced, okay, then you could say they're balanced or equal. And same here. I'll move this down so you can see what the heck I'm writing. Okay. Boop. I'll straighten it out. Now, here's the final part where we actually derive the formula that's on that you use in your lab, whether you realize it or not. Where is it? Here we go. Okay, so if you start with the reference tables, this little formula here, where is it? Says the force of friction equals mu Fn, where Fn is the normal force, and mu is the coefficient of friction. That is a measure of how much stickiness there is between the block and the surface. All right. And keep in mind that you can look up how much sticky, like that coefficient of frictions for many things on your reference tables, okay? But in this lab, we're actually calculating it. But the truth is, the way they get these is by doing experiments exactly like this one in real life. Okay, so it says, since mu equals F over Fn, and all I did was take that formula from your reference tables, and I rearranged it to get mu equals force of friction over force normal. But in this lab, you are not directly measuring either force friction or force normal. You're directly measuring the applied force, and you can calculate the force gravity because force gravity equals Fg equals mg. So if you take the mass and multiply it by the acceleration due to gravity, you'll get force g. So since we actually know force g and we know force applied, that's how we have to figure out mu. But since force friction is equal to the size of force applied, I can rewrite this equation and say force friction is like force applied, and force normal is like force gravity. Keep in mind, this is not always going to be the case, but it's the case here, and we proved it with our free body diagram. Now, one other thing. Mu has no sign and no unit. The reason it has no unit is because a Newton over a Newton cancels, and you get a naked number. So mu should be a naked number. All right, it has no units. It also has no sign. So when you get to the actual lab that you're going to be doing, you are going to have values for force applied and force, and you can calculate force gravity by multiplying the mass that you chose by 9.8. And then once you get your data, you can put in these forces. Okay. And yeah, I think the rest has been taken care of in the lab. Good luck.